Okay, so let's apply our knowledge in our previous videos on NMR and IR to tackle this word problem on NMR and IR spectra. So if you haven't watched the previous video on IR and NMR, kindly go back and watch so that you can appreciate what we are coming today. So we believe that you have the knowledge of or knowledge from the previous videos. So from that, you are going to use to solve this question. So if you haven't watched the previous videos, check on the channel the videos on the NMR and the IR and watch them so that you can receive or you can be able to appreciate what we are about doing. Once again, at the end of this video, I'm going to put that video as the end screen so you can have access to this video. So let's see how best we can apply that knowledge to solve these spectral problems under NMR and IR. So we have this question. It says that while cleaning out a laboratory shelf labeled carboxylic acids and esters, a chemist discovers a bottle simply labeled C5H10O2. To identify the chemical content of the bottle, a sample is submitted for analysis using IR spectroscopy, infrared spectroscopy, and proton and carbon 13 NMR. Enter the spectra below. So how do you understand that question? So let's try to understand the question before you can proceed to solve the problems under it. So it said a shelf was labeled carboxylic acid and esters, as the question says. Now, whilst a chemist was cleaning out the shelf, the chemist found out that there was a bottle which was having this molecular formula labeling C5H10O2. So with this one can be either carboxylic acid or an ester from the question because that shelf is labeled carboxylic acid and ester. Once again, all these compounds have two oxygens as part of their functional group, so it can either be carboxylic acid or an ester. So how do you determine the chemical content of the bottle as to whether it is carboxylic acid or an ester? And if it is an ester or carboxylic acid, how will the structure look like? Now to do that, the chemist sent a sample from the bottle for analysis using IR spectroscopy and proton and carbon 13 NMR. That is very simple. So when he sent for the spectroscopy, we expect to get 3 spectra for that compound. You have a spectra for IR spectroscopy, which is the first one, a spectra for proton NMR, then a spectra for carbon 13 NMR. So the first one, this spectra here, is the carbon or the IR spectroscopy or the IR spectra. The next one, here we can see that this is a proton NMR that is made of, let's try to interpret it. So the proton NMR a plot of the intensity against the chemical acid values on the x-axis. We have 3 signals. This one signal, the next signal, and the next signal. So this one is a signal for TM as the reference. Then the table here gives a summary of the chemical acid values of the signals, the refractive or the peak area, then also the splitting pattern of the various signals in the proton NMR. So the chemical acid value of one is 1.2, the next one is 2.0, the next one is 5.0. Then the splitting patterns in that compound or in the signals, we have the doublet, we have the singlet, this is septet. So these are the splitting patterns. And the chemical acid values here are shown below. Now the last spectra is for the carbon 13 NMR, which has 4 signals. This is one signal, this is the next signal, this is the next signal, this is the next. Take note, this one is not a doublet because from the Pascal's triangle, if this one was to be doublet, these two would have an approximately equal density or equal intensity. So we have this one is not doublet, there are 2 separate signals for that compound. So what does it tell us? The compound or the ester or the carboxylic acid give us 4 signals for carbon and 3 signals for proton. Now these are the questions that we have to tackle under the problem. The first one is we have to base on the IR spectrum to determine whether the compound or the molecule is a carboxylic acid or an ester. Then provide a reason for your answer. Once you have to use the information provided in the proton and the carbon 13 NMR spectra to identify the number of different chemical environments for hydrogen and carbon. Then we have to draw a plausible structure for this molecule. So normally you are going to use the proton NMR and the carbon 13 NMR to do the C, that's the plausible structure of the compound. So let's first deduce the structure if it is either carboxylic acid or an ester before we go forward to find the number of different environments for the carbon and hydrogen. So the first one, if Let's tackle it first. We have to base on the IR spectrum to find whether the compound is a carboxylic acid or an ester. So let's create a space for that. So we have this one. Let's move up to the IR spectra because that's what we're going to use to find if the compound is a carboxylic acid or an ester. Now from this spectra, you can see that you have a stretch for CH, a stretch for CO, and a long spike at this particular wave number, which is likely to be a ketone because ketones displays a wave number at a wave number, or let's say a peak at a wave number range of 1200 and 725 to 1700. So within this range of where we can find a peak characteristic of a ketone. Now the next thing to do is you have to draw the functional group of esters and carboxylic acid. So let's do functional group of ester and carboxylic acid and find different in the bond linkages and see which of them has all the bond linkages displayed here. So when I take an ester, the functional group of an ester looks like this. You have an R group bonded to a carbon with a double bond, then a bonded to O, then a methyl group. So what are the various bond linkages in this compound? I can see C to C bond linkage in all ester because more than one carbon. I can see C to H stretch in this ester because it has a carbon bonded toward hydrogen. I can see C to O stretch, or in this link, this one and this one. Then I can equally see C double bond O. So these are the various bond linkages that an IR spectra of an ester must show. So if I take this ester for an IR spectra, I must see the stretch, or let's say a band, for all these bond linkages. For carboxylic acids, their functional group. So we have carboxylic acid. So we have an R bonded to C, double bond to ketone, now to O. And if you look at this critically, all the bond linkages in the ester are present also in the carboxylic acid. So we can get C to C linkage in carboxylic acid, can see C to H linkage in carboxylic acid, can see C to O linkage in carboxylic acid, and also a carbonyl functional group in carboxylic acid. Additionally, esters also carboxylic acid have O to H stretch. So this is what we are going to use to differentiate between the carboxylic. All these ones are common to all of them. So when I take this one, this compound must have this. So they all have CO or CC, CH, then the rest. They all have it. So we can see that all these ones have this. So they all have the CC, CH, then the rest. But the OH, which is present in an ester and absent in carboxylic acid, let's say present in a carboxylic acid and absent in ester, is what we are going to use to differentiate between an ester and carboxylic acid. When I take the IR stretch, if the compound is a carboxylic acid, I must see a stretch for what? I must see a stretch for this ester, or let's say this OH. If the compound is not a carboxylic acid and an ester, the OH stretch must not be seen. So when I look at the spectra here carefully, I can see that I have a CH stretch, which is common in all of them. I have a long spike at this wave number, which is also present because they all have ketones. I have a CO, which is found at the fingerprint region. Then, of course, I should have also a CH stretch, which is also found in the fingerprint region. Additionally, there is no OH stretch. So if this compound labeled this with this molecular formula is a carboxylic acid, it should have given us a peak for OH. Now, OH of carboxylic acid gives us a very wide peak at a wave number around 3000 to 2500. So this range is where, or even sometimes from 4000 to 2500. So if this compound was to be carboxylic acid, it would have given us a wider peak at this range somewhere here, because OH of carboxylic acid gives us a wide peak at this particular wave number, but is absent, therefore is hence from this we can deduce that this compound with this molecular formula, which we are given as C5H10, let's say H10 and O2, this compound which was given in the question, that is this one, is not a carboxylic acid. It is rather an ester, because if it is carboxylic acid, it will have given us a very wider band, a broad peak at this particular wave number. That is the reason. But the first question says that we have to use the IR spectral to deduce or to determine whether the molecule is a carboxylic acid or an ester. The compound is an ester and not a carboxylic acid, because the IR spectra give us no stretch or OH, which is just specific to carboxylic acid and not esters. That's the first question. Now for the second question, it says that we are to use the information in the proton and the carbon 18 NMR spectra to identify the number of different chemical environments for hydrogen and carbon. So using the proton NMR, the number of different chemical environments corresponds to the number of signals in the spectra. So from this table, you can see that we have 3 signals with 3 chemical shifts, or the signals are shown here, this one, and that one. So here we have that we have 3 different chemical environments for proton. When I come to the carbon, I have how many signals? 1, 2, 3, and 4. So I have 4 different chemical environments for carbon. That's very simple. For hydrogen, we have 3 different environments for the compound, which is an ester. Then for the carbon, we have 4 different environments for the compound. Now the next question is, we are to draw a plausible structure for this compound. That's the most tedious of the works. Now we've deduced that the compound is an ester and not a carboxylic acid. So what particular ester with a molecular formula C5H10, let me rub it. So which ester with this molecular formula C5H10 and O2 can give us 3 signals for proton NMR, then 4 signals for carbon 18 NMR, and also with this particular splitting patterns and these chemical shape values. How do you go by that? Now the first thing is, this compound is a molecular formula. So you have to draw different structural isomers of this compound and see which of them will have this particular spectra. From our knowledge, if we have 5 carbons and ester, then the compound, the isomers form of this molecular formula can be written as this. You can have this one as one isomer. That's an ester, which will look like this. This one will have this same molecular formula. We can have an ester which will look like this. So we just take the terminal carbon and extend with the acar residue. We can have an ester which can also just look like this, with an extension which will go this way, so 3 carbons. All these 3 isomers have this particular molecular formula because they have 5 carbons, 10 hydrogens, and 2 oxygens. Additionally, we can get an ester which will look like this. An ester like this with this molecular formula, or we can also get an ester which will just look like this, just like the way we have drawn the first one. We just come this way, then we extend the oxygen with an isopropyl group. All these 5 isomers, which you can even draw more to this, can draw more, we can even just can draw more isomers of this. All these ones have this molecular formula. Now let's see which of these 5 isomers you want to deduce the possible structure of the ester. Which of these structural formulas will have this orientation? That is 4 signals for carbon, 3 for hydrogen, 10 these splitting patterns for the hydrogen. How many environments for carbon in this compound do you have? For carbon, we have 1, 2, 3, 4, 5. 5 different environments for carbon NMR. So for this one, once again, if you haven't watched the previous video on how to find the number of different chemical environments in NMR for both carbon and hydrogen, check on the channel and watch the video so that you can appreciate what we are doing. This one has 5 different environments for hydrogen. Sorry, for carbon. And hydrogen is 1, 2, 3, and 4 because there's no hydrogen here. So we have 4 environments for hydrogen for this, then 5 for carbon. So this compound cannot give me this spectra. This also have 1, 2, 3, 4, 5 for carbon, and 1, 2, 3, 4 for hydrogen. It is out because we should have 3 hydrogen environments. For this one, I have 1, 2, 3, 4, 5. So 5 for carbon, automatically it is out. Now we are going to deduce, we have eliminated these 3. So which of the remaining 2 will suit this? Okay, so we have this one. The first one gives us how many different environments for hydrogen. We have this side 1. This environment and this environment are basically the same. So we have 1, 2 for hydrogen and 3. So 3 hydrogen environments. Then for carbon, 1, 2, 3, 4. 4. So it tallies. When I come here, I have 1 for hydrogen, 2, and 3. Interestingly, when I come for carbons, I have 1, 2, 3, and 4. So all these ones stand a chance to be our molecule of interest. Now, the next thing to do is, since they all have the same number of signals which corresponds to these 2 spectra, the next thing is you are going to look at the number of the splitting patterns of each of them and see if indeed they all tally with this. So from our knowledge in splitting patterns, from the n+1 rule that we studied in the previous video, when I want the pattern of splitting for this terminal hydrogen, because it has no adjacent hydrogen, the splitting pattern is going to be 0 plus 1. So 0 plus 1, which is what? 1. So this one is singlet. This end is singlet. Do you have singlet here? Yes, we have singlet here. That is this one. When I come here, this terminal here, or this middle carbon here, or the hydrogen on this middle carbon here, has adjacent hydrogens of. We have 3 hydrogen here and 3 hydrogen here. So the pattern of splitting for this hydrogen at this encircled one is going to be 6 plus 1, which is what? 7. Septet. Do you have septet here? Yes, you have septet here. Now the ends here, this one and this one all have the same environment. So they are being split by the 1 hydrogen at this center. Therefore, we are going to have the splitting pattern to be what? 1 plus 1, which is 2. So the pattern of splitting in the second molecule is 1, 7, and 2, where is singlet, septet, and doublet. So we have singlet, septet, and doublet. Wow. Now let's check for the second one. The pattern of splitting for this end here, just like the one we did here, is going to be doublet. The one for this one, just like the one we did here, is going to be septet. The one for this one, just like how we did, is going to be what? Singlet. Singlet. Okay, so from here, we can say that all the 2 compounds here, all these 2 have the same number of signals and the same splitting pattern. So the splitting pattern of the first compound and second compound are all the same. They all have doublet, septet, and singlet. The next thing to do is we are going to look at the chemical shift values of the various signals and see which of them tallies best with this. The chemical shift values of this and see which of them tallies best with this. Now, from our knowledge in the previous video, we stated that when you take an NMR spectra, the x-axis is the chemical shift, then the y-axis is the intensity, as is being displayed here. Now, the smaller or the region of smaller chemical shift is where we have the TMS, that is 0. Where we have a smaller chemical shift values are where the most shielded nuclei are. So if here is 0 and here is 10, this end is of smaller chemical shift value and the shielded nuclei are found here. This end are of the largest chemical shift values and the deshielded nuclei. Next, Let's go back to our proton NMR spectra and observe something. When you look at the three signals here, the septet here has the highest chemical value. It means the septet is the most deshielded, followed by the singlet and the doublet. So a trick to be able to identify that which of these two compounds, either this or that, is a suitable structure for that or this ester, is ask yourself which of them has the septet to be the most deshielded. The one with the septet to be most deshielded is the one which structure was possibly going to give you this spectra. Let's come to our diagram. Okay, let me clean this one so that we can. Okay, let me come here. Let's scroll down. So we want the one which has the septet to be what? The most deshielded. Because the most deshielded one is going to give you the largest chemical value. So the one which looks like this, or the one which looks like this. Which of these two has the most deshielded septet? When I take the first one, the region of the septet is where? This is the region of the septet. When I take the second one, this is the region of the septet. So what I want is, which of these two gives me a septet of what? The highest chemical shift. Or which of these two has a septet which is the most deshielded? Now a deshielded nuclei is the one which is more closer to an electronegative element like oxygen. So the deshielded one is the one which is more closer to an electronegative element like oxygen. Let's come here. Now realize that when you look at this end and that end carefully, you can see that this septet is more closer to the oxygen than this septet. So you expect this septet here to be more deshielded than this septet, because this septet, the carbon here or the hydrogens on this carbon are, let's say, 3 bonds distant from this oxygen, but the hydrogens on this carbon is just 2 bonds distant from this oxygen. So you expect this septet here to be the most deshielded, then this one will be less deshielded as compared to this. Now, since our diagram gave us the most deshielded signal to be the septet, when I come back to where I am, the one which will give me the most deshielded septet is the possible structure that gave me that spectrum. Therefore, this compound gave me the most deshielded septet because its septet has its septet, which is this one, is the most deshielded. But with this, the most deshielded one is the singlet. So if I'm to draw a signal for this, for the first diagram, I will have a graph like this. Now the most deshielded one for the first one will be the singlet, followed by the septet. Then the next one will be what? The doublet. So here is the singlet, the septet, and the doublet. But for the second one, the most deshielded one is going to be what? The septet. Because the septet is the most deshielded one which is more closer to the oxygen. Therefore, for my question that draw the plausible structure for this molecule, my plausible structure is going to be this compound. Now, thanks for watching. Don't forget to subscribe for watching so you can receive every bit of update from this channel. We are going to put at the end of this video, at the end screen, the previous videos on the NMR. Make sure you watch those videos, or you can go back on the channel to check before you start watching this, else you won't appreciate the solution to the question. Thank you.